because now we are going to start discussing Maxwell equations, and which will lead us to things like relativity, radiation, etc. So now we are standing on chapter 7 of Griffiths, and the topic will be not only Maxwell equations but also Ohm's law. So these are the two topics that we will cover, and the main thing is in the first part is to formulate Maxwell equations, and there are two ways to formulate them. One is in matter, which contains all the different currents, and the other one is with the fields E and B. So there are two formulations, and we will have to discuss the difficulties in the two formulations and the differences between them. But eventually they give exactly the same physics. It's not that there are two physics, but there are two sets of equations that you use depending on context. If you have a physical matter that has polarization and magnetization, then of course you will use Maxwell equations in matter. And if you are in a vacuum, high energy physics, radiation in free space, then usually you use only the fields E and B. And you need to know how to jump between them and understand the meaning of current and the meaning of density in Maxwell's equations. So this is what we are going to discuss. So let us start by a kind of reminder what we know up to now from electrostatics. So what do we know up to now? We know that div D. D was the displacement field, so now I'm working in matter. It's related to the field, the usual field E. So if there's no polarization, this is E essentially up to some constant. This is equal to rho free. So the F here is for free charge, charge that can move around in space, what you think about, that generates usual currents, not other types of currents like polarization currents, etc., that I'm going to discuss later. We have div B div B equals 0, and div B equals 0 means, this was explained previous lesson, there are no magnetic charges, no monopoles. This one is of course Gauss law, which is essentially Coulomb's law. Then we have sorry? Yeah, so this is one of the misleading or complicated things in this issue, that when we formulate Maxwell equation in matter, we have four fields, D, H, B, and E. And there are relations between them, and then this is how it is formulated. So soon I'll explain this. And this is, in my opinion, some of the difficulty, but it's not real difficulty, it's just the notation difficulties that eventually you solve. Then we have Kel E equals 0. All this is valid only for electrostatics. Kel E equals 0 implies that we have a potential field. This is obvious from the Coulomb's law, as we explained many times. And then we have Ampere's law, Kel H is equal J free. So these equations were explained, and to understand them, of course, we need the definitions or connections between B and H and E and B, and the polarization and magnetization fields. And these are given, these are just definitions. D is equal to epsilon 0 E plus the polarization field, and H is given by B over mu 0 minus M. So just to remind you, what is P? Capital P, this is the polarization field. So we have a material which has a lot of small dipoles in it, and I look at some region in space, and in this space I have some dipole density. So I count how many, I sum up all the small dipoles, and then I get the dipole density This is this P. And what is this M? You think about a material with small loops or spins or whatever they are, and these add up to this magnetization field, whatever it is. And these enter in these definitions of D and H. Yes? Because I'm recorded, and then and I want to.
So you want the Chinese people to understand, yeah?
I assume I know that some people are sitting at home and listening. So my hope is that this is a small crowd and there are many people watching me, and the course is not going down the drain. This is the reason.
Okay.
And I hope you don't mind.
No, I don't mind. Just.
How many people are watching? Do you know?
Well,
maybe later they will listen. Maybe they'll fast it forward and they will listen. So I'm still a little bit optimistic. That's the point. I know that some people, they can listen to the course at 10 at night. Why do they need to listen right now? Okay, so now this is the static picture that we understood, or we studied, and now we want to add electrodynamics. Electrodynamics means that the currents are in principle time dependent, or the charges here are changing in a complicated way, and then all these fields that are written here, D, B, etc., at this stage are independent of time. But in real life, things depend on time, and that is Maxwell's equations will describe the same fields, but when we have time-dependent phenomena. Yes?
לא הבנתי למה ניסחת את זה באמת עם D, B, H ו... B. כאילו, או שנעבוד עם B ו-E או D ו-H. למה העירוב הזה?
It's the same thing, because you just plug this inside here. For example, take D and plug it into this equation. We'll soon do that exactly. But then you will see what is this. It will be related to the polarization also. So you can do two things. You can work either with all of these equations. If you want to work only with E and B, you need to change the definitions or add two definitions of rho and J. So the meaning of the J will depend on what are the fields you are using. And all these formulations are the same. Do you understand that? You look at me like it's too early in the morning. So the question is, I can put this guy, and I'll soon do that. What is the advantage of this formalism? That here you have this rho F and JF, and then if P and M are equal 0, then you plug it in here and everything is trivial, right? Some people like this rho free and J free because these are the electrons that you can control the movement easily. These are not dipoles that are induced by the external fields. Like P depends on E. If the system is linear, M it depends on B, etc. So here the emphasis, the way I see it, is that you have these two quantities in the formalism. Now you can reduce the formalism, and we're soon going to do that, but then it will not be this guy and this guy, it will be something else. So the poison, you drink your poison in many different ways, and all of them are equivalent, and depending on what is the problem that you have in mind, you formulate the Maxwell equations in different ways. So assume you know these two guys. I think this is the best way to formulate it. You know this one and you know this one. If you know this one and this one, okay, you can reformulate in a slightly different way, and we'll do that. But there's a lot of flexibilities in the equations themselves. That's exactly the point. So let us, before going to different formulations, let us talk about what are the additions that we need. I think you know what there are two additions. What are these? When you go to a time dependent? Yeah, but who are the heroes of the day? One of them is Faraday, and the second one is Maxwell himself. So these are two corrections to the static, or additions, and we are going to discuss them both now. So let us talk about Faraday first. Faraday. So what is the question that Faraday asked himself? what do we know from statics? We know from statics I have some current I, and then I have here some B. This is described, for example, by Babayo-Savat in magnetostatics. Now let us ask the question, how is I created, in principle? By an electric field. You have some electric field that drives the current. So what we have here in electrostatics is some E going to some I, or more correctly to some J. That's the same thing for us right now. And this gives us B, some other place. So now the question is, can we use B to generate E? That is, can we go from B, control B, and give us E? And the answer is that you can control B. How will you control B? You change the current. So this current was static. Now you'll change the current, and then you'll change B. And what will happen? You will create this electric field. That is the question or basic idea of the starting point of Faraday. But he, of course, did much more than that. He quantified this. So the quantification is based on simple experiments that you already saw, that are also discussed in Griffiths. So we have a region in space, and let's assume that magnetic field is going into the wall, and assume there are different types of Faraday experiments. One of them is very simple and taught in high school. So the idea is the following: you take this system, this is a resistor, you close it and you move it here with velocity v. And there is a magnetic field here B in this box that is coming into the... So when you think about it, what will happen? What will happen is, if this is V, B is going into the board. So if there are charges here, the force will be towards up, and then there will be some current. The current will go like this. This is the right-hand notation of these type of problems. But what is actually happening here, because of this velocity V, you are changing the magnetic flux through this loop. And this is the more general formalism. So the change in magnetic flux, the change due to the velocity, creates electromotive force and creates currents. This gives you an effect. If you have a current, it means that you created electric field. This is what we said here. You are changing. So the answer of Faraday in these simple terms is, you need to change the magnetic flux in order to induce an electric field. That in the lab, what we do, we see the current. That is what we see in the lab. Usually we measure the current, but not only. I mean, you can do many things. So this is only one way to create a magnetic flux. I have a velocity here, right? I can do it differently. I can change the magnetic field itself and not move the system. So I can take, for example, this B is created by some solenoid and it has some currents, and then I can increase the currents. Let's say I increase the current uniformly, it goes up in time. That means I'm changing B, and if I'm changing B, I will see a current going, not the current that generates the B, but I'll see a current going through this resistor, which I can measure, and then I can calculate. If I know the resistance, I can calculate also the electromotive force. I can measure all these things. So this is the basics of Faraday's law, and we can formulate it with an equation, and this is the way we were going to do that. Is going to we are going to define this motive force. This is how it's called. I'm not going to say it's good or bad. Is it a force? It's actually kind of a potential, actually. This is EDL. I'll explain this soon, the best I can. Actually, this is very deep equation. This is Faraday's law. This is equal to minus. This is definitions d phi dt. Okay, so there are 1, 2, 3, 4 parts of this equation, and let us try to discuss them the best I can. So this E is similar to what? First of all, what do we have here? This loop is physically this loop, but in reality it can be any ampere loop you want in free space. But if you want to, so there are two ways to refer to it. One is in just some free space and you define the loop. And then this loop is also this surface here, the same thing. And there is a freedom of choice, but another way, maybe more physical, is to go around the loop that is created in the laboratory in a physical experiment. These are two different things, of course. So what is going on here? Where does this E enter in previous things? This is the same E which you called, where is it? What is a different way to create this E? Not by this change of the flux. Called the battery. A battery creates, and there the energy is due to some complicated chemical energy that you create. This is the same E. So this is the E, if you want, that in high school is equal what? I times R. This is the Ohm's law, I times R. This is the same thing. This is the same thing. What we have here, okay. So this is this thing. If I know this E and I know this R, then I know the current through this thing. That's its definition. But why do we define it like this? We define it as EDL. So first of all, EDL, when we have statics, is equal 0. And then you see if this thing is not time dependent, then this guy is 0. And the usual thing is that this integral, the static case, is this integral is equal 0. But now we are not static, so it's not 0. What is this EDL? What is this thing? What does it represent physically? Well, it represents what it is, but what is it? Why is this? What is this? Beside EDL, of course, I mean. This, I claim, is the work done on the one charge along the loop. Why? What is E? So what is this charge? A charge is a tracer charge that I put in addition. So what is this telling you? I mean, what is F on the charge? Maybe this way is a better EQT, tracer. F, I'm going to write as Q times E. And assume there's a problem here, but it's a very subtle thing actually. F is equal QE. And then this is F divided by Q. So this is the force done along the line per unit charge, per some Q. Okay, so this is the work. But is it the work? Is this equation correct? What do we have here? We have here magnetic fields and we have here electric fields. So now, in principle, I can add plus the magnetic field but I'm going to say that this is not important in this equation. Why is it not important? Because the magnetic force, when you calculate the work done here, right, this is the usual equation for work, V cross B, then you go over a line and then the L is V dt, and then the magnetic force doesn't do any work. So this is why I am left with E. Is this clear why the magnetic force is not important? For calculation of the work of this integral. Clear or not clear? It's simply because QV cross B dot dl is equal qv cross b v dt along the path that I'm going. This guy is going to be equal 0. So there is no effect of the magnetic field because of the special dependence on the velocity. So this is the work. Now, this work usually E comes from a potential, usually. And then it's conservative. And then this integral will be 0. But now it's not conservative. And this integral is something. Why is it not conservative? Because we are changing B. We are changing B. How are we changing it in the laboratory? We are changing some J that creates this B. And when you want to change the currents that create B, what are you doing? You need to pump in energy to increase the currents because they are working against some dissipation. So there's no simple conservations law at this stage. Okay, so this is a EDL. But maybe you say, wait, I want to add. No, okay, so what is BDS? I think this is clear. You take the magnetic field and we have this, let's say this type of surface, and we have this ds. So ds is going out, bds, I sum all of them. This is the flux phi. This is the definition, and it has to change in time in order to give this thing. So this, I think, is very clear. How can it change in time? It can change in time by changing the magnetic field, or it can change in time by making the surface smaller. So if I move the surface now here, and then I go move it here, then okay, now in this part there's no magnetic field, so I reduce the flux. This, I think, is very clear. But now the question is, if you go back to your history, where is Ohm's law? I mean, I said this is IR. But how do you see it from these equations, if you want these equations to wake up? Where is Ohm's law? I mean, this is a, I mean, what I mean by Ohm's law, we know that eventually you like to measure current. Let's say you like to measure current. Here there's no current, but where is the Ohm's law here? Or how will the usual way you connect between electromotive force and current pop up? So what is happening here is that there is Ohm's law, and I'm going to write it now as the following. The J, which is proportional to the current, is equal to the field times divided by a constant called sigma. This is not charge density. I'm going to discuss this Ohm's law formulation in detail soon. Sigma is a property of the material. So different material will have different sigma. This is the conductivity. 1 over sigma, the resistivity is 1 over this, so it's a bit confusing, but this is the sigma. So now, if this, this sigma E, I change it because here this one will be J divided by sigma. So here you see that this E, let's write it here, is also the integral over J divided by sigma dl. And this is the current. This is what IR, this is nearly the current. Why is this Ohm's law that you are familiar with, but with some different formulations, because this is proportional to I, right? The usual I that you measure. But this formulation, now you need to ask, why do I bother with this J and not write I? I will explain that in detail because the two formulations are different, and the one with J is deeper, and in many cases really needed. You cannot use I in many cases. In very simple cases, like if this resistor is just a narrow channel that is not changing its width and things like that, you can use I. But in more general case, you need J. But I think you can easily see that this E is proportional to I if J is proportional to I. This is my point. And what is all the rest that comes out? That's what you call resistivity. And that will depend on many things, like the geometry. It's not a universal thing. It depends on the size, blah, blah, blah. It's very complicated in principle. Unlike, for example, sigma, that is a property of material that is independent of geometry. And that's why we do not like this I so much, and we don't like the R so much, and we prefer this one. So just to repeat it, we have here the electromotive force, EMF, it's called, or קם בעברית. It's related to this field. The field is not conservative. This gives you also J that is measured in laboratory. This equation is, however, more general. It's not only for this ampere loop, which is a physical ampere loop. It gives you the flux. We call this flux phi. And then from this experiment, this is an experiment. This is not something I can prove from first principle. It's Faraday is an experimentalist, one of the best ever. I'm not claiming I can really prove this to the bitter end, but I can make sense to things that you are familiar with. And now what we look at is at these two equations. And we are reminded by some mathematical theorem. Here we have integration over ds, and here we have over dl. I want to go from dl to ds. This is called Stokes. And to do that, if I go to ds, it means I have to introduce here derivatives, or just from units point of view. And the units are, or if you do it rigorously, this will be, what will it be? It will be the curl, actually. So from Stokes, and there's a big jump here. The jump is that Faraday is doing it on a real circuit, and now we are doing it in some space. It's an assumption. It's a proposition for an equation, but this is what we are doing. We say there is some ampere. You know, we don't need these resistors anymore. They're not there anymore. We're going to throw them away. It's true for these experiments, but it's more general. And then from Stokes' law, what we get is rotor E. I hope you see this, because if this will be ds, I'll have here minus d dt b. This is what I will call, sorry, Faraday's law. And you see what is it doing? Here I'm saying curl. Here I have curl, and now I have an additional term. So the potential, the usual potential, is not a good thing because, again, because the magnetic fields are changing in time, and then you are pumping energy, and all these conservative, simple conservative potentials are not working anymore. So we corrected this. So Faraday experiments corrected this equation. Okay? So now we are done with Faraday in principle. Of course, to solve this, okay, we have 7 more classes, 6.5. We will do that later. But now we know what is Faraday's corrections, and it is based on E and B only, no P, no M. Maybe some of you are very happy because of that. So now we want to discuss Maxwell's correction. So let us do that. צבע. מישהו יש לו נייר? אולי זה... כן, יש לי. מגבון עם אלכוהול או?
מגבון הלוח?
כן, אתה רואה שנשאר צבע קצת.
מגבון הלוח? זה הורס את כל ה...
תלוי, זה יכול להרוס, כן. אבל אנחנו יכולים לעשות ניסוי. זה... לא, זה בלי כלום.
לא, זה המגבון. זה המגבון.
בוא נראה אם זה...
אל תתאמן.
קצת כושר על הבוקר.
נראה לי זה לא יפה, כי זה מים ועל הלוח.
נגד הספרי הזה? לא חושב ששובר מישהו בצד, נגיד לי
Okay. So now we're going to treat Maxwell. And the correction of Maxwell is based on some basic rule, which is in some sense trivial but very fundamental. Do you know what it is? How does Maxwell correct his own? What is the main tool? Continuity equation. So Maxwell is going to use continuity equation. Actually, this is not correct. Maxwell had all kinds of theories on Aether and all kinds of things. I did not read his original papers because they are written in old Scottish English. It's very, I didn't even try, but according to legend, he uses some complicated theory and eventually he writes at the end, and these equations satisfy the continuity equation. I'll explain that. And today it's the opposite. We use the continuity as a justification of Maxwell. So, okay, the history is as usual very complicated. And what we are going to say, what is the continuity equation? I'm not going to, this was discussed already. I have this free, this is just, you have some current of, let's say, mass or charges, and then this current is changing. As usual, let's say it's something here and then something less there. So in the middle you are adding mass or charges. This is well known, I'm not going to discuss it. It was discussed already in our course. dp free dt. And you see, these two are, this I'm answering you. You are now in your cell phone, but this guy. You see now, this continuity is for these two things. That's why I want them and not other things, which will become later. So, what do we have here? Okay, let us present the problem. That's electrostatics. We have Kel H equal J free. So this is the problem. I'm just defining a problem. Let us assume that this is valid also for electrodynamics. Just the first guess. We are building the theory now. So what we are going to do is we're going to say, okay, what is div Kel H? Well, this is div J free. But what is div Kel of some function, whatever it is? It's 0. So this guy is 0. But this div G free 0. Sometimes, but mostly in general, no. So if the rho free dt is 0, which can happen, there's no change of the free charges, everything is fixed, then okay, we are happy, there's no problem. But in general, this is not 0. So 0 is not 0 if you have a time-dependent free charges moving around somewhere. Problem, right? This is a problem. So how does Maxwell fix this? So what is his proposition? It's just a proposition, but it's a beautiful proposition. He says the following. Let us write this like this. Div Kel H plus div J free. This is 0, right? So let us now write the continuity equation. So I write here plus the rho free dt, and this is equal 0. So 0 is equal 0. Everything is okay, right? Okay, but it's also trivial. Now what? What shall we do now? What's the next step of Maxwell? It's one of the most famous moves in physics ever. Really, it's an unbelievable force of art. Maxwell says the following. You see, I have here a div. I want to have a div also here. Not because I'm a diva, but because I like a div. So he looks at this equation and he says, here there is a div. And this is rho free. So let us assume that in electromagnetism in general, time-dependent electromagnetism, let us assume that this thing is still correct. He's throwing things. It's one of these rare events where physicists are just just guessing in some sense, I think. So this I can write as equal div j free plus, I'm taking it from there, td div. And so this comes from Gauss. Yeah, remember that the first law, you want to call it Coulomb, it's also okay. Gauss, Coulomb, this one. So this is Gauss. This is what I mean by Gauss. And now it has to hold in full generality for all currents J free, for all displacement D, for every field H. So okay, let us assume that it holds for what's inside the div. So what we get that curl H is equal J free. This we know that it cannot be plus some constant, right? Because the div will be plus a constant, because we know that this is true without a constant for the static case. So there's no issue with a constant plus dd over dt. And remember that D is defined over there, it's related to the electric field and the polarization field. So this is maximal addition. This displacement vector, which is proportional to E and the polarization field, gives you something that adds up to the free charge carriers that are moving around somehow. So this is Maxwell's corrections. Okay, this is not so. So now we have Maxwell's equations, and I'm going to write them just so you can see them. Maybe you hate. No, yeah. Do it like this. Div D equal rho free. Curl E equals minus dB dt. This is Gauss, this is Faraday. This is the correction that we added here. Div B equals 0, no monopoles. Otherwise someone will get a Nobel Prize. No magnetic monopoles. And finally, curl H is equal J free plus dd over dt. Now, in these equations, we have two equations which contain only E and B and no sources, and two equations with sources, but they contain D and H, and everything is tied up by this definition here. In principle, go and solve these equations, of course with boundary conditions. That is not so easy. Let us, however, now reformulate these equations slightly. As our friend here said, whoa, this is damn nasty, we have here so many notations. Let's try and reduce it to E and to B only, without H, M, P. Okay, that's what we want to do now. And then we'll have equations for E and B only, but what will change? Rho free and J will change, and their meaning will change. So what are those? Those will depend on these guys. So you'll have a more elegant equation, only E and B, and some J and some Rho, but these J's and Rho are not free charge moving, they are related to magnetization, polarization, and all this stuff. That's the second formulation. So to do that, let us just briefly, what are we expecting? I mean, Okay, we already discussed this a bit. Or let us write here H equal B over mu 0 minus M, and D is equal epsilon 0 E minus polarization field. These are the this is plus, sorry. So let us remind ourselves what I was discussing in previous classes. So, for example, in the context of the magnetization M, what did we say? We said that we have a material with all kinds of currents, but these currents are not flowing all over the place, but effectively they are, for example, on the surfaces or inside the bulk. And we had, due to this magnetization, which again, the magnetization is the sum of many small magnet moments or magnetic moments. What is the JB here inside? It is given by this thing. I hope you remember this. If this M has a curl, then you have some JB. What was this JB? This JB gave you some current that you needed for Ampere's law. Yeah, you remember this, I hope. And then if I have a material with dipole moments, so I have a polarization field. So again, I looked at some volume, I sum up all the small electric dipole moments, I have some polarization field. And then I have, what do I have here? I have rho B. B is for bulk, rho B. This was the polarization field with a minus side. Again, I hope you remember. If I have I have here more dipoles than here, then effectively we have more charges on top than on the bottom, and this will create some charges. And again, this was used inside, for example, Gauss's law. You need this charge. So what I'm going to do now, I'm going to assume, I don't know what is M in principle. You need to tell me what is M to know what is this JB. You need this P field to get this rho B. But these are going to be important in the Maxwell equation beyond the rho free and the J free. That's the idea that we're going to use. And then we will see that there is some asymmetry that we will solve soon. So let us now rewrite Maxwell's equation. We have all the equations, we have them here, or nearly all of them. You'll see that we need a little bit more definition. So we want a Maxwell's equation for E and B. So let us look at div D. Div D is equal to rho free. But on the other hand, I can use the definition of div D and just plug it inside here. This is div epsilon 0 E plus P. Right? But what is div P? It's minus rho B. So I'm going to put this on the other side. I'm going to put this one on the other side. So what do I get? I get the following. I get div E. I think you can see this is, I'm going to divide by epsilon 0. This is just the permittivity of the free space. And here I have rho free plus rho B. Now, we define rho free plus rho B as some rho, some density, which depends on space. And then this is this Gauss law, which not too much has changed, because this is a static law essentially. There's no time here. But what did we learn? That this rho is not what you thought in high school, maybe, or I don't know, maybe you are still at high school. But this is composed of two things: one of the polarization part and one of the free charge part that are moving around. But of course, it's true that now we can just say, okay, we have some rho. But to find, if you want to say what is rho, you need to know the free charges and you need to know this rho b, and that means you need to know the magnetization field. If this is the input to the theory, you need to know the polarization of the field. You need to know the polarization. So I'm hiding here inside something that is in general difficult to say what it is. We are cheating. Not cheating, we are not cheating. This is the real physics. What I'm trying to say is many problems will tell you, here, take some rho, solve this. Yeah, but what is this rho? This rho is built out of the polarization field, among others, if you have matter. Okay, so this is equation number 1. This was the Gauss law. Do I need to change this one and this one? The answer is of course not, because these already depend on E and B. So I only need to look now on this equation, the last one, Ampere equation with Maxwell corrections, and see how it is formulated with E and B. Okay, so let us just start writing it here. Maxwell's equation for E and B. So we have here div E equal rho over epsilon 0, rho equal rho free plus rho b, and we have div b equals 0, not a problem. We have curl E equal dB dt, that's again Faraday. And now we need to do a massage to this last equation, to Ampere plus Maxwell correction, to formulate it in terms of E, and then there will be some subtlety. So what do we expect? And this is indeed what we will get. You see, this one depends on JF. Now what will happen when I add these definitions? Instead of JF, I'll have, oh, it was here. It somehow has to be related to JB, which is the rotor of M. But there is something more to it, and this is what I'm going to show you now. But this is what we are expecting to head to. So let us see how this works. This is very bad. Okay, so curl H this is this one. I'm just going to plug in curl B over U0 minus M. You see curl M? It's exactly what I said before. What is curl M? That's the JB. I'm happy. So this is equal J free. This is just this one. But now I have this D. This is something a little bit different. This D is E0 E plus P. Right? Because the D is composed both of the electric field and the polarization field. That is, this thing is, what is that? So let us organize this. I want to write it as a curl B equals something. So curl B, I multiply by U0 and go to the other side, is U0 times JF plus JB JB, this is simply curl M by definition that we had already. plus something I'm going to call JP. That is the new thing for you new. What else is equal to U0 from here, epsilon 0 dTE. What is this time? This is the usual connection of Faraday, right? I mean, this is A. But now I have a new current. There is a third current. So there is a total asymmetry here. There are 3 currents, and how many densities? 2. So I didn't define it yet, but it comes from d dt rho. So what is this one? JP by definition, 3 lines is a definition, is dp dt. Physically, what is this? It's a polarization current. That is, the polarization itself has a field, and then it changes in time, and then you get this new current. The question now, soon I'll answer this question, is it justified to call it a current or not? How do I answer this question? What do I mean? Is it justified to call this a current? How would I mean, what? No. Current of something you can always write in any units. It's not a Q over T. It's certainly not. But of course you can check the units. That's also correct. I'm not saying not. But what does a current need to satisfy in university? Maybe not in high school. But the continuity equation. We need to think, why does this thing satisfy the continuity equation? I mean, you are creating. Yeah. Okay, the polarization is moving around in a very complicated way in principle, and then this creates this thing. Okay, but so this is the definition. And now, if I'm going to call all this J, the sum of this, then I have curl B equal U0J plus U0 epsilon 0 d dt. And this is what we wanted with this price. So I have here curl B is equal U0 J plus U0 epsilon 0 d dt E. So this is ampere plus Maxwell, and I already said what are these, the people behind this. And what is J, however? J is J free plus JB plus JP. So people like to write the equations in this form. Why? Because they can hide in rho and in J all kinds of dirty details of the theory. But when you want to solve it, you need these dirty details, because especially if there is an M and there is a P, then okay. But of course it's also true, let's say that M and P are equal 0. There's no dipole moments, there's no magnetic moments, that is, you are not in a material. Then these equations are very elegant, there's only J free, that is fine. These are great equations, I'm not saying they're not. I'm saying that you need to understand the equations as a basic inside or outside. They are complicated in this form as they were in the previous form, but you put this complexity in these definitions of J's. Okay, so now there is a small problem, or maybe big, I don't know. Here there are 2 densities and 3 currents, which is very strange, right? I mean, you expect 3 and 3, what is going on here? Where is the, why don't you have here another density going with this JP? That is the question. So we will see that this simply always vanishes. So I'll formulate the question in a slightly different way. Does this J, and this rho, do they satisfy the continuity equation? What do you think the answer is? Of course, yes. Otherwise, I wouldn't call it J and I wouldn't call it rho, but let us check or see why this happens, and it's, again, a bit strange because you have this symmetry breaking. These Maxwell equations are very strange. So let us look at div J, which is equal to div J free, that's just the definition, plus JB plus JP, the current due to the polarization. This, remember, from the magnetization, this was the rotor of M. Is this, question mark, equal to minus ddt rho, which is what? Which is minus ddt rho free plus rho b. That is the question. So if we look at these equations, what is obvious? I mean, maybe not obvious, or we actually said it already.
Div JP equal to 0.
Yeah, this is what should happen, but what is obvious is that this guy and this guy correspond one to another. We actually said it already, but this is just conservation of my material. So I can throw away these two guys. I hope this is clear. This is just the usual continuity equation. Now, what do I have about, what is JB? Remind ourselves, it's rotor M, right? So what is div JB? Div of a rotor is 0. So this guy also goes away. So what do I need to prove to show that this equation is correct is to show that div JP is actually minus ddt rho b. So this is polarization rho b. Remember, rho b was also related to the magnetization. How was it related to the magnetization? You should remember this. To the polarization, sorry. This was simply d over t div p. And what is this one? I'm just using the definition. This is div p dt. Div p dt. I can put the dt here. There is a minus sign here. It's a plus. And you see that 0 is equal to 0. So the conclusion is J and rho, which is the total density and the total currents, satisfy the continuity equation. And this comes from, where did it come from eventually? From the fact that rho b was the div of P. So when you apply div to this definition, you get the same answer. So it comes from the definition of rho b as div P. So everything is working, and at least from a point of view of a theoretical physicist, this is a proposition which is nice, and it's beautiful, and it's actually correct based on experiments. This is Maxwell's formalism. Eventually, things work. The continuity equation is holding. We don't think anything serious is violated. Of course, there is a small problem, and that is to solve these equations. And we are going to solve these equations from different forms from now till the end of the semester, essentially. So let us have a break. And after the break, I'll discuss a little bit the Ohm's law, which is not related to time dependence, but I used it already to justify the Faraday's law. I'll discuss a little bit Ohm's law, and yeah, this will be our lesson for today. So now we want to discuss a little bit Ohm's law.
אפשר לפני שאתה ממשיך לשאול את ה... הרי הגדרת, איפה זה? את ה-DP ל-DP. אוקיי? שזה ה-JP. מה זה בעצם אומר?
זה אומר את הדבר הבא, יש לך איזושהי מערכת, יש לך פה P מסוים, באזור מסוים, וממה הוא מורכב? מסכימה של הרבה דיפולים חשמליים, ועכשיו אתה פשוט משנה את זה בזמן, אתה מזיז את זה איכשהו, אתה לוקח פטיש. אוקיי. Why is this defined as a current? I showed in the end of the class because it is defined as a current of in the sense of the continuity equation. In that sense, so this will satisfy the continuity equation as I mentioned, and then anything that is coming in and out, you can put in some polarization, you can take out some polarization, and this is related to this continuity equation. You don't create dipoles out of nowhere. That's the point. You just move them around. Yeah, but it's a subtle issue. So now I'm going to discuss the Ohm's law, and I'm going to discuss the Ohm's law. I'm going to try to relate it to the famous Ohm's law that you know from high school, and the Ohm's law that we use in the third year in undergraduate, and show you the differences, show you when they agree and when there are real pitfalls that show advantage of the more advanced Ohm's law, let's call it this way. So when I mean more advanced Ohm's law is I mean the following. We have the current density J is equal sigma E, and sigma again is the conductivity. The sigma, you can go to some textbook or you can go to some tables, and sigma will depend on things like temperature, density. It's super complicated. Most people in condensed matter physics study this as a function of external parameters. This law by itself is a phenomenological law. It's not a basic law of nature, and there is a hidden assumption here. What is the hidden assumption? That the electric fields are small enough in order for J, the current, to satisfy this law in such a way that this sigma is independent of the electric field. So Ohm's law is by certainly not a fundamental law. In principle, if you go to strong fields, you create all kinds of heating effects. It's much more complicated. But in many materials, the electric fields are weak enough in such a way that this is a fantastic approximation, and we work with this one. So this is a weak field limit, but again, when I say weak, in a practical sense, these are covering many situations in physics. The other formulation is V equal IR, which again I want to explain the connections between these two equations, and immediately you see some of the connections, but they are written in a very different way. So this E is obviously related to this potential, this J is obviously related to E, and sigma is related to R, but it's actually much more complicated than these things. But you see the parallel. I just wanted to say there are three letters, and there are three letters, and there are some connections between these letters, and intuitively you understand that these two equations are connected, right? What is the big advantage or big difference between these two equations? Maybe what? No, also the dimension, yeah, that's the zeroth difference, you are right, but one step beyond that. The big difference, yes? Very simple.
Vectors and the scalars.
These are vectors and these are scalars. Okay, that was -1, that is 0, but my point is very simple. you see, these are all local. Local. These depend on where you are in principle. So if I have, I'm in this point, I have some E, which is a function of x, y, and z. By the way, for now, everything is static. There's no time dependence. So these are, as you said, vectors. These are not vectors. So these are local fields. Now, the question is actually, what is the resistivity? That is not a trivial question. What is R here? So, of course, when you go to some shop, you can buy some slab, and it will tell you this is in ohms, this is the resistor, and this has this and that resistance, because you can measure it with this law. But what is R actually? What is it? It's a property of what? Unlike sigma, R is a property of the geometry, the length, the width, all kinds of things. So sigma is considered the more basic tool that you have, because sigma is a property of the material. So for a given material, at a given temperature, at a given pressure, there's a number, sigma, that we can put for this. And this is valid, this sigma is here, there, etc. If you give me you give me this conductivity, I can calculate these things. So there is a question in general how you go from this law, which is microscopical, to this law. And sometimes when you start here, you do not reach this so easily. I'll explain some cases where it's not so simple, and some cases where it does work, everything is okay. I don't want to say that everything is wrong. In this equation, I just, at the end of the class, I'll show you one example where this equation is, in my opinion, non-trivial, and what it means at all. Okay, so these are the questions. So let us start with a simple example. What else do you know about the basic Ohm law? You know how to add resistance in parallel and in a series, right? You know how to do that. Let's see how this comes out from the basic Ohm law. So let us do some exercise. So we have material 1. And an interface, material 2. And here I have J1 flowing in this direction only. Here I have J2 flowing in that direction. And here I have sigma 1, and here I have sigma 2. Again, sigma 2 are the conductivities, these sigmas. So these are two different materials. And now I want to work in steady state, because this equation is in steady state. What does steady state mean? What does steady state mean?
There is no dependent on time.
Yeah, but no dependent on time. But what does this mean? J1 is equal to J2. What comes in, what goes out. So this will be like in Ohm's law that you are familiar. What does it mean? If J1 is equal to J2, it means that the current I is also constant. There's no, and only then you can apply this. If J1 was not J2, what will happen? You will pile up here charges. So let's say you switch on the field. You create this J1 not equal J2. What will happen? You will create here some charges here. And they will be adding, because what is coming in is not what's coming out. It's like for my class, everyone is leaving. So it's reducing the charges. The charges become, let's say, negative, less students. If it would be 0, it would be great. But okay, anyway. But J1 is going to be, so at the beginning, J1 is not equal J2 when you turn it on, and then you create these charges. So there will be some charges here. I hope this is intuitive. Now these charges, how they are created, I cannot say with this law. Or at least I don't know how to find them. But I can, and I soon will, with this law, find what are these charges that are created in the middle. And then this is an example where this one, when I used it, it gives you a microscopical picture which gives you a prediction what are the charges here. And then you can test it in principle in the laboratory. while this more, I would call it macroscopic. Why is it macroscopic? Because you are averaging. The R is not a local E and not a local G. You are averaging. It doesn't tell you anything on these charges here that are created. So let us find these charges, okay? But is it clear that there are some charges? I hope it's clear, and this is the point. What are these charges? So it's easy to solve this, and then in the following way. Let us use this equation. So we have J1. There's no need to use vectors. Everything is flowing uniformly. This is an assumption, if you want. Sigma 1, E1. Sigma 1 is material 1. What is J2? Is sigma 2, E2. And the fields are uniform. They are not changing in space beyond on the boundary. Now we know that J1 is equal J2 from steady state. So for example, E2 is, what is E2? E2 is sigma 1 E1 sigma 2. It's a relation between these two quantities. Of course, you need to give the J. Let's call J1 equal J. You need to give the J, and then I have E1 and I have E2. You need to know what is this current. But this is also in Ohm's law. You need to know the current in order to know what is these fields. And there's no vectors here. But now, what am I going to use in order to find this charge density here? Gauss law, yes, because again, everything is static, and Gauss law is always valid. There's no polarization here, there's no magnetization here. So I can use a small, this is the boundary here, let's call this x equals 0, small Gauss box, and then the jump in the field, you see E2 and E1 are not the same, unless sigma 1 is the same as sigma 2, and there will be a jump in the field, and that will give me the surface density of the charges that are created here. Yeah? So, but now we have a big problem. What is the problem?
There is 2 sigma.
Yeah, well, not only these 2 sigma, but there's another sigma. So we will denote this sigma as the charge density on this surface. This is the charge density here in the middle. As sigma plus, this is charge density. And let us denote this. This is the Gauss box, the usual Gauss box with size A that I create. Then, as usual, sigma, the charge density times E is E2 times A minus E1 times A, so I can cancel the A's. And I know E2 and I know E1, and then I can easily, by plugging in these numbers, I can say what is the charge density. It is 1 over sigma 2. 1 second, 1 sigma 0 times J. Yeah, there is a missing epsilon here.
Multiplying by epsilon.
Multiplying. Here is multiplied, and I never remember. So, and also here, yes. Why did I forget it? But you see from this equation, which is valid up till some epsilon 0, that if these two guys are the same, this will give you 0, and there will be no charge, and otherwise there is a charge. Okay? Yeah, where the epsilon 0 goes here. And then, okay, please check this. And then we need to fix this later. Yeah, where is the epsilon 0? Sigma is here, I think.
But that's the chart.
Wait, what is going on here? No, this is okay. I mean, E has yeah, I mean, from point of view of units, E has units of Q divided by 4 pi epsilon 0 R squared. So this is Q divided by R squared. So this has, the epsilon 0 has to be here. Yes. Yes, this is what you said. You want to multiply it on the other side. Yeah, so here I have epsilon 0 and here I have epsilon 0. Thank you. So, okay. So now, okay. So what else can I say here? Now we can also see this is a problem of summing two conductors one after the other in line, the two, right, in line, in a series. So let us see that this works. So let us say that this object has a slice here of B. This is the surface, this is the size of this channel, call it B, not to confuse with this A. A was for just the construction of the theory.
Why there is minus between them?
Here?
Yeah, because from the analogy, I get the analogy that it's like summing up
this goes in and this goes out. Because
so like one is reducing and one is going in, right? But we don't get the analogy to summing up resistors in...
I'm going to show it just
okay.
now. And this is not a problem. So we have this thing, and I'm going to define the resistance now, and I'm going to define the summing.
Okay.
So what is J? By definition, in this problem, it's I over B. This is just the definition of the density. This is all, and this is equal J1, and this is equal J2. Now, what is the potential? The potential that we all know from the Ohm's law, that is EDL. And this EDL will go from 0 to B, to L, sorry. And this is 0 to L. So in order for us to even define the resistance, we need to define the size of the system and its width. You know this, the longer the system, the bigger the resistance, right? So this is why we don't like this so much here. This doesn't enter. But of course, in practical applications, this L is important. So now we have this integral. I can divide it into two parts. I need to define the system, L over 2, L over 2. This is just a choice. So this is material 1. This is material 2. I could divide it in a different way. This will not be a problem. This could be 1/4 and this is 3/4. It's fine. You'll soon see why. Because what is this in this example? This is E1, L over 2, plus E2, L over 2. This is what it is. So this is a connection between potential, electric field times L. These are, of course, of the right units. But that's it. It's not with R. We don't see still R yet. But this is easy now to find R. Why? Because we can use these equations to define E1 and E2 in terms of J1 and J2 and define here the following. So I will have here L over 2 in this example. The E's are proportional to J, right? But here I have 1 over sigma 1 plus 1 over sigma 2. This is a connection between J and V, but what do we want? We want a connection between I and V. So I need to continue. This is L over 2, 1 over sigma 1 plus 1 over sigma 2 I divided by B, which is this equation. So what is the resistance in this case? This is Ri, first of all. And what is R? It is L over 2, 1 over sigma 1 plus 1 over sigma 2 divided by B. If sigma 1 and sigma 2 would be the same, this 2 would vanish and then we have L over B, which was something I think you know. But you also see here that this is exactly the addition of two resistance. This is R1 plus R2, where R1 and similarly R2 is L over 2 sigma 1 times B. So this is adding in a series. We get it from the basic equation, and then what you paid for high school, the money you paid there, you don't need to get back, but you didn't pay anything, so it's okay. So everything is working here, everything is as usual, but we did get something new, and that is these charges here that we can see in this formalism, which we could not see in the previous formalism, right? I mean, I don't think you can see it easily with IR, so we have this. This is the new thing, if you want, that we added to the basic laws, which are elementary. Questions? Now we want to do a different, we are not going to solve this, but I'm going to solve a problem that is solved in many textbooks, and it's totally wrong. Or not totally wrong, but very wrong. And this is a problem, maybe you solved it already. And here we will see the pitfalls of Ohm's law. So I want to solve in principle. This is a cone that looks like this. This is 2A. This is 2B. And what are we thinking about? We have a potential difference between this side and this side. If there's a potential difference, there will be a current here, right? Because there is electric field, and it will flow. And this field, this material has some sigma. What is the R of this system? So, did you solve this problem once? I'm sure you did. In high school.
עשינו דברים דומים בחשמל.
Yes, okay, not in high school. But most likely, if you solved it, it is wrong. The way you solve it, from a very, it's a bit subtle, and this is what I want to. So, so this problem is given in many textbooks. And the intended answer is incorrect. So I want to first make a mistake, and then we will discuss why what is the problem. So let's say you have this type of problem. I hope you understand that there's a sphere here. Yeah, it's not a two-dimensional thing, it's a sphere here. How would you solve this problem? I mean, in principle, and we'll soon solve it. I mean, this is a very well-known method that in first year is solved. So, you don't have any idea how you solve these problems? I mean,
integrate all the...
Right, integrate what?
I think sigma. Over the volume.
Let's say you didn't hear about sigma.
You can find dr.
Yeah, dr. So, okay, so let us define things first of all.
Integrate over.
This is 0 to L. And then if I look at this object, I'm going to say, let's divide it into slabs. What are these slabs? These are circles, right? They're coming out. And then I have here dr1, and then I have here dr. There's a current going on. What do I need to find the r? I have to calculate dr1 plus dr2 plus dr3, etc. I have to add it, and then I'll get the resistance. What is this? How is it called, what I'm doing here? In a series, חיבור בטור. But it doesn't work here, that's the point. It's wrong. So this answer is wrong. But let us see what is this usual way of solving things. Later we will see why it's wrong. So, yeah, so I define here, this is x. So the radius r of x. So again, this is some x, this is 0, this is L, and this sphere is coming out of you, and there's a radius here. Let's do it like this. This is the radius Rx. It's very easy to prove because we know this point is between 0, this is x, and there is this opening here, right? Which depends on this A and this B. I'm not going to prove it, but it's I'll simply explain it. This is A plus B minus A x over L. So when x is equal 0, you are here, the radius is A. When x is equal L, the radius is B, which is at the end. And in between, you see this is a straight line. This is a line of a straight line. So if I know 2 points, I know the line. So this is, I actually proved this. This is the radius that you are opening. As you go here, you become, if B is not equal A, you are opening up. This is the angle. So how do we solve this dr? What is dr? So one of these elements, one of these, let's call them plates. What is dr? It's 1 over some sigma, that is a property of the material, times delta x over, let's call this A of x. And what is A of x? Yes, this is 1 over sigma dx pi r squared x. That's it. This is dr. Now, in order to add them in series, what do? I want to calculate r. I need to integrate dr. This is the meaning of sum dr1 plus dr2. Sum this up, I need to do this integral. So this integral is 1 over sigma, integral from 0 to L dx pi. I need to write down what is this radius, B minus A.
אבל אמרנו שזה לא נכון, לא?
All this is wrong. Wrong, okay, let's be a bit more careful. It's an approximation to reality.
Okay.
But we need to understand why it's only an approximation. For example, there is one case that is perfectly correct, which is B equal A. This is correct. So if B is a little bit smaller than A, this is a good approximation. If B is much bigger than A, it's a bad approximation. So, and then we'll later see why this is wrong. Or what we need to do in order to solve this type of problems. What is the difficulty in solving these problems? I'm actually not going to solve it because no one can solve this problem. You need to solve it with a computer, but that's a different story. Okay, so I need to do this integral. And this integral is trivial because it's something, a constant plus something times x. So I do this integral, then I'll get 1 over sigma, then I'll get times pi, then I have a plus b minus a x minus 1. And then when I will take the derivative, I need to divide by b minus a, 0 to L. It is very easy to solve this. I'll just write the final result. R equal this L sigma pi AB, which, you know, as L is increased, R is, when L is longer and longer, then you get this increase with L. This is A times B, but it's a bit complicated because you see, as L becomes bigger and the angle is fixed, B depends on L. So it's a bit non-trivial result. Again, this is sigma pi A multiplied by B. And this is a really a well-known solution. Now let us start seeing what is wrong with this, or where we might be wrong, because from here it's very difficult to say why is it wrong. Maybe you can say, why is this wrong? I don't see. I mean, we just assume that you can add them series, and then, okay, we plug it in and we do this. But let us see what is the meaning of adding up things in series based on this equation, and then
Maybe there is no continuity.
continuity of what? Of the current, you mean? This is one problem, yeah, but
maybe it's not constant, so we not can to
what is not
get
constant?
it out. I mean, the electric field, because what we do is
But in this formalism, there's no electric field, but
No,
you are correct.
to find the resistance, we do this integral for the potential,
Yeah.
and we
Yeah, so this is essentially the field, the equipartition lines in these type of problems are very complicated. And for example, and also this what was stated previously, you are not creating currents. But let us soon I'll explain this a bit better. Let us solve the same thing again in the wrong way, but and then not using this. So here, what did I do? I just used the. Let's sum up in series and we get this result. This is what you do in first year. Okay, now you're a little bit more clever. You use this equation, but you can still make mistakes. Let's make another mistake, the same mistake. But then this will teach us something. I hope you don't mind that I make mistakes, because for mistakes you learn how to do things correctly. So let us assume that the assumption here was on the addition of resistance. Now we're going to assume something else, which is equivalent. And that is that the current is constant. Let us assume that current is constant. Let us see where does that lead us. So I is a constant. So if I is a constant, what is I? It is integral j ds. That's a definition. And I kind of have here this slice, and I can calculate this I. But if it's a constant, then this is equal to some j of x times what? Pi rx squared, which is similar to what we had here before. So here, the Jx, all the current is assumed everywhere the same. It's just one current. This is hidden in this equation because there's only one current here. There's no local currents that depend on x and y, right? We threw that away. That is the problem, actually, one of the problems. So, but let us say the current is constant, so we know, okay, Jx is this I pi r x squared. I just put it on the other side. Then I know from Ohm's law. But now, so what does this say? You know, the bigger the radius is, the less the J. This is very obvious. So here you have the same current. So here I have a strong current density, and here I have a less current density. It makes sense if you assume the current is density. That is okay. And what is this? Then Ex is simply I just divide by sigma pi r x squared. And this is the field. And then I can say, okay, what is the potential? Now I need to do the integral from 0 to L EdL. Why do I want the potential? Because I want to define the R. Without that, I cannot, this is a function of x. I cannot see the R right now. I need to do this integral. But this integral is exactly the same that we had here. I think you see it because here I have R squared. It's exactly the same thing. So if I do this integral, I get, of course, the same result. I get now I, this I, V equal I, and I get something. And the something is exactly what we had here before. It's L sigma pi BA. This is what we call R. Depends on the geometry, depends on sigma, etc. So by doing this, we did gain something because we started discussing the current and thinking about the current. What is the problem with this current? It's all in one direction. So let us look now, for example, on the boundary. So what is happening really with the constant? What does it mean constant current going in one direction? Which would be true if A would be equal B. What is happening here? This is Jx here, Jx. It depends on x. So this is for some x. Right, this is Jx. And here there is another Jx, Jx1. But you see up here especially, it's very strange. Why is it strange? You have a boundary, and from nothing, you start create a current. Where does this current come from? What is div J? Now, it's not impossible. It is possible. This solution is correct. When is it correct? When some guy, if you put some guy here, and he injects currents from here in a very crazy way that maintaining the constant, then this solution is correct. But this is not what is meant in physics, because in physics, what do we have here on these two boundaries? We have insulators. There's nothing going out, nothing coming in. We have potential in the entrance, 0 at the end, and no currents going out from the other two sides. This is what is meant in physics. So I'm not saying that we cannot imagine a situation like this, but it is, in my opinion at least, very unphysical situation. And not what is meant, and not what is measured in laboratory, because no one is going to have these small people on the boundary injecting currents in this direct way. Unless you are crazy experimentalist, maybe you want to do that because you want all the textbooks to be correct. Okay, so they are not correct because of this. So now comes the main point. How do we solve, in principle at least, this problem? And what was missing fundamentally in the strategy of solution?
אפשר כמה שצריך פה להניח שהזרמים הם לא רק במקביל, אלא גם הולכים באלכסון, ואז משם מגיע הזרם הזה?
Yeah, in principle you can do that, but it's not so obvious how in this geometry, the way the current is going is super complicated. No one can solve it in this geometry unless you solve it numerically. So there are currents, they are not going in this direction. How are they going? Let us first answer, we cannot find it, no one can find it. There's a numerical paper from 1996, which is only, maybe for you that's a long time ago, but not so long ago, which solved this problem. I can send you to these references if you are interested. But let us first just state, we need to define the problem. Up to now, in this, there was no real definition of the problem. How do we solve the problem with this one? So the main idea in this type of problems is just the following. I need to define what is very important. I said this a million times. Boundary conditions. If you do not define the boundary conditions, you get all kinds of, let's call it nonsense, or approximations. You cannot go anywhere without the boundary. The boundary conditions are everything. So what are the strategy to solve things? The strategy to solve things is, let's say I want J, X, Y, Z. Why do I want J, X, Y, Z? If I know J, I can calculate I can calculate the relation between J and the potential difference here. But what do I actually do when I solve these J's? Do I like to solve J? How do we get J? You get it from E. Oh, okay. So I'm not going to solve for J, I'm going to solve for E. And how do I solve for E?
I think that you can solve the Laplace equation.
Yeah. So what you do to solve these problems, you need to solve the Laplace equation, which is what we started with, Laplace. Why? Because there's no charges here. I mean, this is an assumption, except for those on the boundary. Now we need to define the boundary, and there are two boundaries here. One here and one here. So let us say you say this is a potential V, which is a constant here. And let's say here it's 0. So you have a potential. This V, this delta V will enter into the eventual. You will solve for E, you will find J, you will integrate E in order to get this. You'll get this I, and then you will find this R somehow. What else is missing? The two boundaries on the top and on the bottom. What are the boundary conditions in this problem? The reasonable boundary conditions. Of course, mathematicians cannot really answer this question because every boundary condition is a physical boundary condition. You need to tell us what is the boundary condition. So what is the boundary condition? J equals 0, that's a good point, yes, and then, but we don't want J, we want E. We want E. So J is equal to 0, E is going to be 0, and that is the normal of the potential. So what we want is that dV dN, this is normal is equal to 0 and also here. Because dV dN will give you the electric field. The electric field that way gives you what? Gives you the current, but there's no current, so that's equal to 0. N is a normal to this line. The derivative in this direction, not in this direction, for example. Okay? So now you see the problem of solving this. Why is it difficult? Because in this direction I have spherical symmetry, and in this I have, let's call it Cartesian symmetry. So there's no solution known in a closed form. You can put it on a computer and you can solve it. Griffiths gives a different problem. So if you can't solve one problem, you solve it numerically. Fine, but you can also invent easier problems which are related and that you can solve. And an easier problem that you can solve with the same boundary conditions is to define something like this. Radius. I hope you understand what I mean. So we have one radius here, and they come from the same point Here I have V and the same boundary condition. This is a solvable problem, but this problem is not the same as this problem because of the difference of these two lines here compared to these two things. This is given as an exercise in Griffith's book. I can give you the equation, but you can find it there. So this is solvable, this is unsolvable.
What is the difference?
Yeah.
There is on the radius and here is...
Here I define the boundary. You need to define the entry to the system. And this is here a line connecting these 2 points.
and
This is a line. And here it's a radius. So if I continue this to here, I have here a radius on which the potential is 0. So it's a slice of pie. Yummy. Yeah, this is a pie, and this is a straight.
למה את זה אי אפשר וזה אפשר?
It's not that you cannot do it. You can write an infinite series, and you can sum it up, but it's an awful infinite series.
it's like spherical in each
Yeah,
direction.
exactly. This one is spherical in each direction. You see spherical, spherical,
Spherical.
and spherical over here. So you can see, I'm not saying that you can understand why you can solve this one, but I'm telling you can solve it. It's an exercise in Griffiths, but you see the symmetry here compared to this one. This is, at least intuitively I hope, is easier because of spherical, spherical, and round spherical. This is why this one is solvable and this one is not solvable. This one. So, what? Yes.
A lazy question, is this an example or a problem in the book? Like, can we see the answer? It's a problem.
He gives the answer to this. I can also give you the answer because I copied it.
Because I'm looking for it and I can't find so.
It's the end of chapter 7. Yeah, end of chapter 7 in one of the questions.
Okay, thank you.
So, you can make a competition between the different methods and 1 second. Yeah, so if you are interested, I mean, this you can find, this is Price and Romano. American Journal of Physics. '64-1150, 1996. So we have 3 methods, or three approaches. One of them is based on summation, what we do in first year. You have this problem, and you have this problem. Let's say that this is the correct problem. So what happens here, first of all, with respect to the current? The current goes like this in this problem. So it's not like what we said before. Here the current is going out like this. It's easy. In this problem, it's not so easy. It depends. There's a different behavior here compared to the middle. But we can compare the 3 approaches, and we can ask, let's say, A equal, if I remember, 2A equal B. You can plug it into, let's say, you can plug it, I tried this, you can plug it into ChatGPT, this problem, and you can ask ChatGPT to solve it. What does ChatGPT do? First of all, it solves it like in high school, gives you the wrong answer.
Yeah.
Then you tell him, no, this is a mistake, because you did learn something, so you know it's a mistake, and then he says, okay, it's a mistake. Then you tell me, okay, then he says, can I solve it numerically? Then I said, yes. He said, please solve it numerically. He gives me the wrong answer again. And then I ask him, why did you, but this is a contradiction to what is said, they say, in this paper and in Griffith. You are correct, because in my code, I built it in such a way that the currents are going all in this direction. Then I said, okay, correct that. Then he solves, I don't know what but he gives you some result, which is different than this result. You can do it semi-numerically in this way, but of course you need to be very careful not to believe what is said there, but at least he can, I mean he or she or whatever, God or whatever, can give you a hint, and then you can draw the equipotential fields or the currents based on this program. Of course, don't trust ChatGPT, but it gives you this intuition that, okay, maybe something is going on here. But if you want, you can go to the original paper, or you can build the code. And then for this geometry, you can calculate R, and then this is not so big. This is only 2. If it would be 4, it would be much bigger. Then if you calculate R, so this is, let's call it high school method, deviation of 10% only. 10% from what? From the exact numerical result. This is the deviation. And for this strategy, R from here is deviation of 3%, which is much better than 10%. Compared again to the exact numerical result that you get. So you see some differences, and if I would be more, the deviations will be more. Now you can ask, is it important, 10%, 3%? It's not so important. It depends on, exactly, I mean, it depends on the details. But this is not my point. I don't care about it. I mean, any real resistor will fluctuate because of temperature and many other things. So, okay, but the point of view here and the summary is very simple. We need to define the boundary conditions. We need to calculate E. From E, we can calculate J. They come from the Laplace equation. Solving the Laplace equation, we did in the first part of the course with all kinds of methods. I'm not going to do it again. This is all valid in static limit. There's no time dependence here. So Laplace is not only helping you solve the static problem, they help you to get the currents under the assumption that Ohm's law is valid, which means not too strong fields. I mean, there is an assumption here. This is only a linear response theory. And then, yeah, things can become very difficult very quickly, but that is life and that is the truth. So, okay, so here we finish for today.
Sorry, also, if the size of the cone is very big, can you also approximate?
This comparison, as far as I remember, is done for large L. Because otherwise, what they do is they increase L, and then you know R is going to be proportional to L. All these basic things work in all these models. It's very simple. It will be proportional to L. The question is, what is the number in front of this L? So they increase L. They find the resistivity up to a number. In all cases, they are proportional to L, but the number in front will deviate by 10 or 3% from the reality. And I think L small will not work at all. Okay, see you then.
Thank you.
Next week.
להסתכל לאינטואיציה.
לא, לא כתבתי, זה בספר.
גם לאינטואיציה שלי, אנחנו נקבל פה פונקציות בספר. מה אתה עושה? סתם, בלי לפתור, כאילו, לאינטואיציה.
לא, הפתרון הוא שכתוב אצל גריפיץ, הוא להר.